dealing with the fluid. So the respiratory system deals with fluid that is gas. So we know that fluids are come in two forms. They come in the form of a liquid like the blood. The blood is a liquid fluid, while fluids are also gases, and air or oxygen and carbon dioxide, air, that is also a fluid. So if you are liquid fluid like blood, then that's the responsibility of the cardiovascular system. And we said that the cardiovascular system is actually the heart plus the blood vessels. The heart plus the blood vessels. While if you add to the cardiovascular system actually the blood that it's pumping, that is no longer the cardiovascular system. What is that called now? What is that called now? If you have a subway station and subway tracks, but no people who are taking the subway. Circulatory system, excellent. So if you have the heart, the blood vessels, the cardiovascular system, and you add to that the blood plus the blood, you add to that plus blood, that is going to give you circulatory system. That is known as the circulatory system. So that's the responsibility of your heart, your blood vessels, and the blood. Dealing with a liquid fluid. But we have a different type of fluid, and that is the gas fluid, air. Removing carbon dioxide from your body. Carbon dioxide is a form of metabolic waste. So carbon dioxide is a form of metabolic waste, and carbon dioxide increases the acidity. Carbon dioxide increases the acidity, and that makes a lot of sense because we have carbonic acid. So carbonic acid increases if you have a lot of carbon dioxide. So an athlete who's running the marathon, what is happening? They are hyperventilating. They are shunting so much carbon dioxide out of their body because carbon dioxide is generating at a really fast pace. Carbon dioxide is piling up in their blood, increasing the acidity in the blood. So in order to restore the blood pH, so our blood must have a homeostatic range. Everything must have a homeostatic range. Remember when we began this course, we said that for temperature, you don't want hyperthermia, you don't want hypothermia, you want euthermia. For blood pressure, you don't want hypertension, you don't want hypotension, you want eutension. For sugar, you don't want hyperglycemia, you don't want hypoglycemia, you want euglycemia. Same thing with the pH. The pH of the blood, there is a U, but we don't call it UPH. And the pH of the blood that is physiological, that is healthy, that is homeostatic. So homeostatic, healthy pH is actually from 7.45. That's the upper limit, and the lower limit is 7.35. That is your healthy homeostatic pH. If you drop below 7.35, that is known as acidosis. Acidosis. That is known as acidosis. If you drop below 7.45, and if you go above 7.45, that is known as alkalosis. alkalosis. That is known as alkalosis. Acidosis is below 7.35 and alkalosis is above 7.45. So now an athlete who's running the marathon, and when they are running the marathon, their skeletal muscle system, these big muscles that are helping the athlete running around so fast, so strong, slamming the ground. These arms that are helping the athlete coordinate the movement. Because they're moving, they're gonna need energy, and that energy is provided from breakdown of food products, breakdown of carbohydrates, breakdown of proteins, breakdown of lipids and fats to get ATP, to get energy. Well, this metabolism, this active breakdown of these metabolites is going to generate waste. And one of the forms of the waste is your carbon dioxide. So we said carbon dioxide is going to diffuse into the blood in the form of what? Carbonic acid. Carbonic acid. So carbonic acid is going to pile up in the blood. Carbonic acid is going to pile up in the blood, and then that athlete, their blood is going to become acidic. So in order for the acidity to go down, if you want to go up, we need to get rid of the carbon dioxide. So what's going to happen to the rate of breathing, the rate of exhaling? What's going to happen? It's going to increase. So now that athlete is going to hyperventilate. The athlete is going to hyperventilate to shunt and remove carbon dioxide out of the body, and then we're going to be able to restore our physiological pH, because we got rid of the carbon dioxide, the carbonic acid that is piling up. Then what about the opposite? What about somebody who is not suffering from acidosis, is not suffering from so much carbon dioxide? They are suffering from too little carbon dioxide. They're suffering from too little carbon dioxide. Is that acidosis or is that alkalosis?
Too little acid, alkalosis.
Acidosis is when you have too much carbon dioxide, and that's why you need to get it out.
So you made an arrow down, no?
So if you go, the arrow down here means that you went below 7.35. You went below, if you go below 7.35, that is known as acidosis. If you go below that. So what does acidosis mean? Acidosis means there is too much carbon dioxide. Too much carbon dioxide. Too much carbon dioxide. It means there's too much hydrogen proton. Too much hydrogen proton. So in order to repair that, we need to get rid of the too much carbon dioxide. We need to get rid of the too much hydrogen proton. So what's going to happen here, there's going to be hyperventilation. Hyperventilation. There's going to be hyperventilation. There's going to be hyperventilation. It's going to be hyperventilation. So you're shunting away carbon dioxide. You're throwing away the carbon dioxide. Does that make sense? So, one more time. Acidosis happens when the blood becomes acidic. How do we know the blood becomes acidic? Is when the pH is less than physiological pH. When the pH is less than the lower limit of your physiological homeostatic pH, 7.35. If we go below that, that is acidosis. We see this a lot with athletes or somebody who is exerting extraneous exercise. So why do we have acidosis when we're exercising? It's because our muscle cells are using up so much metabolic products. They are they are participating in aerobic respiration. So much aerobic respiration is happening, so much oxidative phosphorylation is happening, so much metabolism is taking place to supply energy to the skeletal muscle cells so I can maintain my running. But obviously, if the cells are taking so much energy, if the cells are participating in this excessive respiration, then they're going to be generating some metabolic waste. The cells are going to be generating metabolic waste. One form of the metabolic waste is the carbon dioxide. So the more your cells are excreting carbon dioxide into the blood, that carbon dioxide is going to become carbonic acid, and it's going to make the blood acidity so high. And this blood acidity is going to become so high because the pH is going to drop 7.3, 7.2, 7.1, 7.0. That's really dangerous. So in order to resuscitate, in order to help yourself return to the normal level, what happens is all your systems, but today we're not doing all the systems, we're only doing respiratory system. What's going to happen is your respiratory system is going to start to remove, exhale this carbon dioxide. And the more you hyperventilate, throwing out carbon dioxide, there's going to be less carbon dioxide in the blood because we removed it through the lungs to the outside of the body, and that's going to now decrease the acidity, and the pH is going to go up until we reach physiological pH. Does that make sense? Now, in the other opposite scenario, you have a patient who does not have really acidic blood, does not have too much carbon dioxide, has too little carbon dioxide. So they are suffering not from an acidic blood, they are suffering from a basic blood. They're suffering from basicity. So that means the carbon dioxide for a patient who is suffering from alkalosis, is it going to be low or is it going to be high?
Low.
Carbon dioxide
Low.
for a patient who is suffering from alkalosis
Low.
is going to be low. That also means the hydrogen protons, are they going to be high or low?
Low.
They're going to be low. Don't just say high, don't just say low. Think about it. Acidosis, like carbonic acid, so that means carbon dioxide will be high. I wrote it here. Carbon dioxide will be high and hydrogen protons will be high. That is your acidosis. But for alkalosis is the opposite. Carbon dioxide is going to be low and hydrogen protons are going to be low. So now, to resolve that situation, what is your respiratory system going to do? Hyperventilate? Hypo. So here we did hyperventilation to get rid. So let's say that this is our mouth. We're going to hyperventilate to get rid of this carbon dioxide. To get rid of this carbon dioxide. We want to throw away the carbon dioxide to clean our blood, to cleanse our blood from carbon dioxide. Now, if we have alkalosis, we're going to do hypoventilation. So we're not going to be throwing out as much. We're going to throw out very little and keep the carbon dioxide in, so that when carbon dioxide stays in our blood, our pH is going to become more acidic, which is what we wanted. We had alkalosis, in negative feedback, you repair with the reflex, with the opposite. When you have hyperventilation, when you have acidosis, you want to increase the pH. But when you have alkalosis, you want to decrease the pH. So you want to take measures that repair this deviation from homeostasis. This is my normal, 7.45 to 7.35. 7.45, 7.35. If I go above that, If I go above that to alkalosis, I need to do something to return down, which is hypoventilate, to keep the carbon dioxide in my blood so that my acidity can increase and my pH returns. And here I hyperventilate so that I remove carbon dioxide and my pH goes up. So a patient who has acidosis will have a pH that is below 7.35, like 7.25, 7.15. That's dangerous. So I'm going to hyperventilate, remove carbon dioxide from my blood, and the more I hyperventilate, the more my pH is going to increase until I reach my safe zone of physiological pH, then I'm done. And here, if a patient is suffering from alkalosis, that means they went up from 7.45 to 7.55 to 7.65 to 7.75 and so on. So now if I want to repair that, do I want to go up more or do I want to go down? If I want to repair that, do I want to go up some more or do I want to go back down? So I want to go down. So what's going to help me to come down? Hyperventilation or hypoventilation? Hypoventilation. Because when I hypoventilate, I'm not going to throw out as much carbon dioxide. I'm not throwing out as much carbon dioxide. I'm going to keep in the carbon dioxide. And when I keep in the carbon dioxide, my blood pH is going to drop. And my acidity is going to increase. And then I'm going to return back to the normal region. Okay, so now this is the job of my respiratory system. Removing carbon dioxide when it's too much and keeping it in when it is too little. And also for oxygen. Don't forget that the respiratory system is not only dealing with carbon dioxide. The respiratory system is bringing in a lot of oxygen and removing a lot of carbon dioxide. We are bringing in a lot of oxygen and we are removing a lot of carbon dioxide. So we have two types of respiration. There is an external respiration and there is an internal respiration. So if I ask you on the exam, what is the difference between external respiration and internal respiration? What is the difference between, everybody wrote this? Okay. What is the difference between internal respiration and external respiration? Okay, so this is us. And these are the lungs. Okay, so there is oxygen in the air, so that's the air, and these are the lungs, and that's my tissue. That is my tissue. That is my tissue. That is my tissue. That is my tissue. Okay. What happens is I need to be able to bring in oxygen, from the air into my lungs, then exchange oxygen into my capillaries, Bring in oxygen into my capillaries, then deliver oxygen into the tissue. So external respiration is when I bring in the oxygen into my lung and I exchange the oxygen I got from air with my capillaries. This is external. This is external respiration.
Can you say it again? Bring in
Okay,
oxygen.
sure. External respiration is when I bring in oxygen from the air into my lungs, or when I throw out carbon dioxide into the air from my lung. Carbon dioxide goes out and oxygen goes in. Carbon dioxide goes out. Carbon dioxide goes out and oxygen comes in. So when oxygen comes in, we need to now transfer oxygen from our lung into our blood, circulation, And we need to take from our blood into our lungs the carbon dioxide. And then we throw the carbon dioxide out. So here, if I'm bringing air, I'm bringing oxygen in my lungs and throwing carbon dioxide out of my lungs. That's external, because I'm dealing with the external environment. That's external respiration. But when I deliver the oxygen, the blood to my tissue, this is my tissue, this is my body. My skeletal muscles need oxygen. My epithelial tissue need oxygen. My bones, they need oxygen. My blood cells, they need oxygen. Okay? The adipose tissue needs oxygen. Your nervous tissue needs oxygen. Tissue is a bunch of cells, so they cannot live without oxygen. They need aerobic respiration. They need oxidative phosphorylation. So when the oxygen gets to the tissue and your blood says, here tissue, that's oxygen, we just got it from the outside. And then the tissue says, can you also take away from me this carbon dioxide? It's making me so acidic. It's making acidosis. That's internal respiration. That's internal. Internal respiration. That is internal respiration. So internal respiration is when I successfully deliver the oxygen that I got from my external respiration to my tissue. And when I successfully remove the carbon dioxide from my tissue out into the external environment. So remember, respiration is a two-way. It's not just oxygen. It's not just carbon dioxide. It's both. It's when I bring in my oxygen and remove my carbon dioxide. Okay, so who would like to tell me the difference between the internal respiration and the external respiration? Yes.
So, external respiration happens when we bring in oxygen from the air into our lungs and take out the carbon dioxide from our lungs out into the air. And then we use the external respiration for the internal respiration when we take the carbon dioxide out of our tissues and bring in the oxygen we got from the air from the external respiration.
Excellent. Perfect. That's a perfect answer. And you can tell internal because I'm dealing with tissue. My tissue is internal. My tissue is internal. So if I'm exchanging with my tissue, that's internal respiration. If I'm exchanging with air in the outer environment, that is external respiration.
Can you write that? Can you write everything you're saying?
Okay. So, external respiration is when I'm exchanging gases with the external environment. So respiration, what is respiration? Is when I'm exchanging both. I'm taking the good oxygen and removing the bad carbon dioxide. I'm taking plus the good oxygen, that's positive, and removing the toxic minus carbon dioxide. But where is that happening? That's the question. If I'm exchanging, I'm doing this either way. I'm getting good oxygen, removing carbon dioxide. That's bad. But where am I doing it? Am I doing it with air, the external environment? Then that makes it external respiration. But if I'm doing it inside my body, exchanging with my tissue, saying tissue, you have a lot of metabolic waste building up. You have so much carbon dioxide that's piling up. That carbon dioxide is going to become carbonic acid, increasing the acidosis, converting your blood pH to really low pH. Okay, going below 7.35. So that's acidosis. So if the exchange is happening downward, you know when you have an Amazon shipment that you bring in, you're buying something from out of the country. That's an external shipment. You get the shipment from Europe, from China, from India, then you get it to the US. That's the external shipment. But then when you transfer it from the airport through Brooklyn or Queens or Staten Island, that's internal. You're inside. So look, in order to tell external from internal respiration, you have to understand where it's happening. But the same thing is happening. It's not like in external respiration, you're sending out carbon dioxide, bringing in oxygen, but in internal, you're sending out oxygen. No. Respiration is the same. Oxygen is taken everywhere, and carbon dioxide is removed. But where is it? Who is participating in this exchange? You also have to know the gradient, that this process is happening based on gradient. Remember when we began the course, we talked about diffusion. Diffusion is based on a gradient. Diffusion is based on a gradient. Remember when we said you have two slabs, slab A, and slab B. And what happens in slab A and slab B? Slab A maybe is 500 degrees Celsius and 100 degrees Celsius. We said there will be a diffusion from a high temperature to a low temperature, and both of them will equilibrate at 500 plus 100 divided by 2. That's 300 on each side. And then what happened was that was a thermal gradient. What kind of gradient is that? What kind of gradient is that? That's a thermal gradient. Now let me replace the 500 degrees Celsius with 500 millivolts and 100 millivolts. And what happens now is the 500 millivolt is going to move to the 100 millivolt until they both equilibrate at 300 millivolt each, 300 millivolt each. What was that an example of? What kind of gradient is that? Electrical gradient. That was an electrical gradient. What if I replace the 500 millivolt with 500 millimolars of glucose? 100 millimolars of glucose. So what's going to happen now is glucose is going to move from an area, glucose is going to move from an area of high glucose concentration to an area of low glucose concentration, and both are going to be at 300 millimolars of glucose. 300 millimoles of glucose. So that's an example of what? Concentration gradient. That's a concentration gradient. Chemical gradient. Now with the respiratory system and the cardiovascular system, we're dealing with pressure gradient. So when the heart contracts, the heart has so much pressure. So now the blood is going to flow from 500 millimeters of mercury, 500 millimeters of mercury to 100 millimeters of mercury. From 500 millimeters of mercury to 100 millimeters of mercury. From your heart to the tissue. And same thing when you're breathing. When you're breathing, the air is not going to move except like in diffusion. So for example, when you take a deep breath, what is the direction of the movement? This is really important. What is the direction of the movement of air when you take a deep breath? It goes from one, the air, to two, the lungs, and three, your tissue. You see this order? Air goes in. So then, order for me, the pressure. Is the pressure the highest in the air, or is it the highest in the lung, or is it the highest in the tissue? We said fluid, like blood or gas, is going to flow only from an area of a high pressure to an area of a low pressure. When you squeeze the toothpaste is going to come out from where you squeezed to the opposite place, right? Your heart, when your heart contracts, the blood is going to flow from where it's near the heart to away to the tissue. So the blood flows from an area of a high pressure to an area of a low pressure. The same way glucose diffuses from an area of high glucose to area of low glucose. The same way temperature diffuses from high thermal to low thermal. Do you understand? We move from high to low. So if air is going from air to the lung to the tissue, who's the highest pressure? Air. Who's the second highest? Lungs. Who's the least highest? Excellent. So now I don't say pressure, I say the partial pressure for oxygen. So the partial pressure for oxygen is going to be the highest in the atmosphere. And this is called the atmosphere. We don't say air, we say the atmosphere. The atmosphere. So the partial pressure for oxygen in the atmosphere is the highest when we're inhaling. Then the second highest partial pressure is going to be in the lungs. Then the least highest partial pressure is going to be in the tissue. Now, who can answer this question? What about the direction of the partial pressure for carbon dioxide? The partial pressure for carbon dioxide. So the partial pressure for carbon dioxide. The partial pressure for carbon dioxide. Who can help me with that? Yes. So the partial pressure for carbon dioxide, so I have three compartments. These are called compartments. The air is compartment number 1. The lung is compartment number 2. And who is compartment number 3?
Tissue.
The tissue. So when I'm inhaling oxygen, the partial pressure is highest at the atmospheric compartment. Then the partial pressure for oxygen is second highest at the lung compartment. Then my partial pressure for oxygen is the least high at my tissue compartment. For carbon dioxide, where is my partial pressure for carbon dioxide the highest? The tissue. That makes a lot of sense. Why is that? Because my tissue is generating a lot of toxic, is using oxygen for oxidative phosphorylation. Why do we need oxygen? We need oxygen for oxidative phosphorylation, for oxidative phosphorylation, for aerobic respiration.
Are they the same? Aerobic respiration, respirative.
Yeah. So oxidative respiration is one of the steps in your chain, in your sequential pathway, in your stepwise biochemical cascade in which we have aerobic respiration. So that's how I tell students to remember, why is oxygen useful? Oxygen is useful because it participates in aerobic respiration, particularly in your oxidative phosphorylation. Particularly in oxidative phosphorylation, it is the final electron transport chain acceptor. So you gotta learn that. But for now, we need oxygen for tissue oxidative phosphorylation, and you need oxygen for aerobic respiration. But you're gonna generate waste. You're gonna generate carbon dioxide. You're gonna generate waste. So this waste, this carbon dioxide that is generated, is gonna now be the highest in the tissue. It makes no sense carbon dioxide is the highest in the air, because nobody's making it. But it makes a lot of sense that carbon dioxide is highest in the tissue. Then the carbon dioxide is the second highest in the lung. Then carbon dioxide is the least highest. So if we look at our air, we see that our air, if we count all the molecules in air, we will see that 78% of air is nitrogen. 78% of air is nitrogen. And 20% of air is carbon dioxide. Then 0.0 0.01 or 0.02% of air, 20% is oxygen, and 0.01 or 0.02% that's carbon dioxide. That's how little carbon dioxide is in air, which makes a lot of sense. It goes out from the tissue where there's so much carbon dioxide to the lung, then out to the atmosphere, because there's so little carbon dioxide in the atmosphere. And it makes a lot of sense that there's so much oxygen in air, 20%, so much oxygen in the air, 20% goes into my lung, then into my tissue. So we're always moving in different directions that are fulfilling from highest partial pressure to least partial pressure. So the lung achieves that. How does the lung achieve that? The lung achieves that by modulating, by changing its shape. That is going to be achieved by the lung changing its shape. So when you take a deep breath, what happens to your lung? When you take a deep breath, your lungs expand, or do they get shrink?
Expand.
They expand. So when they expand, the volume increases and air goes in. But when you exhale, you squeeze, so the air goes out. From an area of high pressure, your thoracic cavity, when you exhale, your thoracic cavity gets so small, compressing the lungs, getting the air out. So now you see how the pressure, like you're squeezing toothpaste, you're squeezing your lungs to get the air out. And the air has no problem because it's a fluid and goes from a high pressure to low pressure. So now do you see how your intercostal muscles, how your rib cage, how your diaphragm working together to create this pressure difference? If you want to get air out, your diaphragm will compress the lung, your rib cage and intercostal muscles will compress the lungs, and air will get out. And if you want air in, your diaphragm is going to move away from the lungs, and your intercostal muscles are gonna relax, and they're gonna expand the lung. So the lung is like a balloon. The lung is like a balloon. It's like a balloon. We inflate it, we stretch it to bring air in, and we compress it to get air out. So look at the volume of my lung. Look at the volume of my balloon. When air is coming in, what's happening to the volume? Increasing. Excellent. So the volume increases and the pressure decreases and air moves in. That is inhale. When we are inhaling, the volume is going to increase. When you're inhaling, the volume is going to increase and the pressure is going to decrease so the air can come in. But when you want to exhale, and get the air out, the volume is going to decrease and the volume is going to decrease and the pressure is going to increase. So this is known as Boyle's law. Boyle's law. What does Boyle's law say? Boyle's law says at constant temperature. Does it make sense we have a constant temperature? Yes, euthermia. Okay, your temperature is not, when you get too hot, you're going to sweat to come back to the normal temperature. When you're too cold, you're going to shiver to return to the normal temperature. So you have a constant temperature. So Boyle's law says if you have a constant temperature, then the relationship between the volume and the pressure will be inverse. So now at a constant temperature, your body temperature, you get a thermometer, you put it under your tongue. What's your normal temperature? 37 degrees Celsius. It's not gonna change.
96.90. What is it in the Fahrenheit?
37 degrees Celsius. Fahrenheit is about
97.
97.3. Yeah.
Or something like that. No?
Yeah.
Okay.
So, when your temperature is constant, the relationship between the volume and the pressure is
The opposite?
opposite. That's why when you inhale, the volume is gonna, like a balloon. The volume is gonna, when you inhale, take a deep breath, the volume is gonna increase, but the pressure decrease. But when you exhale, the volume is gonna decrease and the pressure is going to increase. So now when you look at the model, how did this show that?
I have a bean here. They talk about the anything. Let me not be so good.
Okay, if we look at this, what do we see? We see our lung. What is the name of this tube made of cartilage? This tube right here, made of cartilage, what is it called?
Trachea?
That's the trachea. So you must be able to recognize that on the lab practical. That is something that we always ask about. What is this? That's your trachea.
That's what it is.
This is your lung, but you have to recognize your right lung from your left lung. So this is your right lung and this is your left lung. That's the right lung. That's the,
Oh, it's also like switched, just like the heart.
like, this is the right lung, that's the left lung. And the lung is divided into lobes with these fissures. Are you guys paying attention? So, look at the left lung. How many fissures? That's really important. How many fissures does the left lung have?
2.
No, I didn't ask lobes.
Is it one?
Oh.
It has one. It's on the bottom. And it divides the left lung into upper and lower lobes. Superior lobe and inferior lobe. Do you guys see the superior lobe and the inferior lobe? Okay, that's the superior.